part 3 of the slides on water. Right, so we've gone through how water works and intermolecular forces to kind of understand what water does. So now let's think about why do we need water? And a lot of times I ask this question, people tell me to stay hydrated, but that's kind of like saying, well, I need water because I need water. So there's a lot of reasons biologically that we need water. So one of the reasons is water is a great solvent. As long as things are polar, water is very polar, so a lot of polar things dissolve in water. So a lot of proteins are water soluble, not all. A lot of things in your body, a lot of minerals, ions dissolve in water. Your blood has water in it, right? Water is very good at regulating your temperature. You know, when it gets hot outside, you sweat. So water can absorb a lot of the heat. And then, of course, because it has a high boiling point, when you sweat, the heat from your body is used to help evaporate the water. So it's a good example of of water taking heat away. It takes the heat out of your body as it turns into a gas. Also, it's extremely reactive. Water is not an unreactive substance. We don't think of it as being reactive because we like the reactions it does, but a lot of reactions that your body does involve water. In fact, they're called hydrolysis reactions. So just to show you, this would be a protein molecule. R means the rest of the molecule. And when proteins are broken down, when you digest protein, you break it down into, you break this bond here, and see how the water is written in kind of a reddish color? So this oxygen here is from the water, right? And then these two hydrogens are from the water. So it's used to break things down. It's used in hydrolysis of fats when you break down fats, hydrolysis of carbohydrates when your body breaks down carbohydrates, when you make DNA. So it's very, very involved in a lot of the reactions that happen as well. So your body needs water for a million reasons. Now, where do we get water? A couple definitions, whoops. So potable water means that it's safe for human use. So don't answer this right now, but think in terms of, well, do you drink tap water? Do you drink bottled water? What kind of water do you drink? So let's look at where water comes from. Now, yeah, it comes from the store, but realistically, it comes from, comes from aquifers, which are underground lakes and rivers, surface water that runs off into reservoirs or runoff from rain. And so what's in the water? Everything it touches that will dissolve in it. So it comes from rain and runoff or underground stuff. And so if it's an underground lake, it's going to be sucking things out of the soil around it. It's going to have decaying organic matter. It's going to have waste from aquatic organisms like fish and stuff like that. It's going to have dissolved ions. I'm putting the word minerals in parentheses. So minerals are dissolved ions. Any other dissolved polar compounds that might be in water. So there could be proteins from breaking down tissue, right, decaying organic matter, all sorts of stuff like that. So water is going to have a lot of stuff in it. And again, minerals are dissolved ions. And of course, water runs over rocks and soil, and it's going to have all sorts of ions in there. It's going to have sodium, chloride, calcium, magnesium, potassium, carbonates, sulfates, probably some phosphates, all sorts of acetates, hydroxides, all sorts of ions are dissolved in water. These are what are called minerals. So when you read a label and it says it contains minerals, it's a very generic everyday term. And what do these things do? Well, they're very important in bodily function. They regulate neurofunction. So neurotransmission involves a lot of sodium, potassium. At the neuromuscular junction, where nerves talk to muscles, calcium is involved. Calcium ion, these are ions. Calcium ion is involved a lot in cellular regulation. Magnesium is involved in some enzymes. Okay, just to maintain the osmotic balance, so water doesn't come out or float in. And then trace elements. So trace elements just mean very small amounts, like there's a small amount of copper and cobalt and other ions that are involved, but may be very important just in small amounts. So minerals are very important in terms of nutrition because your body has to function. Right. Now, frequently when we test water, and we being probably the EPA, Environmental Protection Agency, when they test water, we know that too much is bad and too little is bad, so you have to have the right amount. And we specify amounts. And a lot of the ways are specified because, remember, solutions are mixtures. So mixture is not a pure substance. That means you have to say how much is there. You can make a sodium chloride solution by putting 1 grain of salt in 15 gallons of water, or you can put 100 grams of salt in 50 milliliters or 100 milliliters of water. Either way, it's still a salt solution. So we specify this way. Percentage you'll see a lot. It's just typically grams over grams. Parts per million, parts per billion. These are used for pollutants. So if you're looking at water testing, there's one of the labs we do on water testing. Parts per million is kind of the same idea, but times a million. This is a part over the whole times a billion. So a part per million is more than a part per billion. Now, how much is a lot? It depends on what it is. So there's an old saying, I brought this up a couple of times, everything's a toxin, it just depends on the dose. So 5 parts per billion might be trivial, or it might be toxic, it just depends. 5 parts per billion cyanide, bad. 5 parts per billion sodium chloride, you wouldn't even know it's there. Right? So pollutant is anything that's not supposed to be there, like a weed. Right? And things that dissolve in water are very hard to get out of there. But anything in the ground that gets into the water has to be removed to make it drinkable if it's bad. So a lot of lead, typically not so much in the ground, but in old pipes, if they use lead pipes, mercury, all sorts of stuff. Drinking water, tap water, if you turn on your tap, it's regulated by the EPA. By the way, San Diego water, if you go to sandiego.gov and you click into the water tab, they have very, very good reports on water. And in the reading assignment I'm giving you, I'm going to ask you to reference it. They do a really nice job. They tell you where it comes from, how they test it, how they collect it. They're really actually very, very good about that. Right. Just to show you where drinking water comes from. So we get it from a lake or reservoir, and it's going to have fish poop in there, right? And then typically it goes into like a big pot, and they'll add what's called a flocculant. And what this does is it's just a solid that's going to sink to the bottom, and it's going to take any particulates in water, any solids that are just kind of floating there out of the water and sink to the bottom. All right. Then it just sinks to the bottom, and then it goes through another process. Then there's some sedimentation, so the heavy stuff gets to the bottom. Okay. Then it's going to go through some type of filtration. Typically in a reservoir, it goes through rocks, and then smaller rocks, and then sand. And that's going to get out all sorts of stuff, except not a lot of things that are dissolved. Right? And then it's going to go into a place where it gets disinfected, and then off it's going to go to the tap. Now, what are disinfectants? Well, we're trying to get rid of bacteria. So there are still places in the world where people get a lot of waterborne diseases like cholera or typhus, and people used to die from that stuff in large numbers, way worse than COVID, because it's really, really bad. And of course, we do a lot of stuff to remove that. So some of the things that are added, chlorine, fluoride, ultraviolet, ozone, or just doing sterile filtration. Now, is chlorine good for us? The answer is absolutely not. But typhus and cholera are way worse, and the amount of chlorine that's in water is not really, it's very, very low by the time it gets to your tap. Remember, too, chlorine's a gas, so it's going to boil, it's going to heat up. Fluoride is an interesting question, and notice it's not fluorine. Fluoride is very, very important for teeth. I would argue that if people have access to fluoride toothpaste, there's really no point in putting fluoride in water. So it kind of depends on where you are. If people don't have access to fluoride toothpaste, it's very important, because if people's teeth start getting sore, they don't eat well, they get infections in their mouth that go to the rest of their body, and again, they don't eat well, so they're nutritionally challenged, right? Other disinfectant methods, running UV through it, ozone, filtration, but it's hard to do filtration on large scale, but that's what RO is, right? Some other means we can do it in small scale, we can distill it. So in a distillation, you heat it up and you turn it into a gas. Anything that's dissolved is going to stay behind. And then it goes into a sidearm here. And then what happens is, this is a gas. The gas is going to go through a jacketed tube. So this is a tube within a tube. This tube is cold. And so then it's going to recondense. This is called a condenser. And then it's going to come out and it leaves all the solids behind. Now this is a benchtop method, but you can do this on large scale. The trick is, it takes a lot of energy to do this, to boil water. So you have all sorts of problems with distillation as a method, or desalination using distillation, because of the energy cost. You can do it on a larger scale. This is just kind of a great big still. Same idea though, you heat it up with a coil, turns into a gas, and then gets recondensed. So desalination is a big deal though, because if you think about it, where does the water come from? Well, if you're sucking it in from the ocean, that means you got to have a giant means of sucking it in, and of course anything else that's swimming around gets sucked into, so it can do some damage to marine life. Right? And then reverse osmosis is a filtration. And so what you're doing is you're pushing, basically you're filtering it, but you use a very, very small pore size, and you push it through several types of filters, semi-permeable membranes, that are so small that ions can't get through. Put it under a lot of pressure. This is an example. Okay. So let's just, a couple of discussion thoughts. You can think about this on your own. Should you drink pure water, deionized water, like the deionized water in the lab? And I would say no. Bottom line is, it's nothing wrong with it, but you need the ions, right? You need the ions. And purified water doesn't have ions in it. So is that a bad thing? Well, do you get ions from other sources? Anything you eat is going to have minerals in it. So food is going to have ions in it. So under normal circumstances, I would say drinking pure water is just fine. Usually people don't. But you don't want to drink large amounts of it. And certainly, if you're running a marathon or doing some very rigorous exercise where you're sweating and sweating, when you sweat, you lose everything that's dissolved in the sweat, including ions. And so if you're sweating out a lot of ions and water, and then you're just putting in the water, it can really screw you up. And so under extreme conditions, I would say pure water would not be a good choice. Under normal conditions, it's really just not going to matter. All right. And then let's talk about bottled water a little bit, because everyone loves bottled water. 20 years ago, if you went to the store to buy water, there was like one little section. Now there's an entire aisle. Interestingly, so bottled water, where does it come from? Well, let's look at a couple examples. So Dasani, which you can buy, that's bottled by Coca-Cola. That's the water that goes into Coca-Cola. I would argue it's probably, I don't know for sure, it's probably filtered tap water. Aquafina, same thing for Pepsi. So a lot of the bottled waters make some interesting label claims. They have all sorts of sources. Interestingly, bottled water, tap water is regulated by the EPA. Bottled water is regulated by the FDA. So it's a completely different agency, but I looked it up, and the FDA basically uses the EPA standards. But you definitely want to be careful. What about the bottles? Okay. Well, the bottles, are made from plastics. I would argue that they're probably safe for single use, even maybe a second use. I wouldn't reuse the bottles over and over again, simply because they're designed to break down, because of landfills, right? Years ago, you put them in a landfill, they would just stay there before we had recycling. So chemists have re-engineered them so that they will break down faster. Of course, the downside is if you keep using them, they'll break down, and some of the stuff that's kind of stuck in there will start leaching into the water. But it's not going to be a big deal. I would say that probably the spit that you put on the bottle when you drink out of it is probably a bigger problem than the leaching stuff. But I wouldn't reuse them more than once. So just something to think about. Tap water, relatively safe, I would think, in general. And what happened in Flint, Michigan was when things went wrong. People knew stuff was wrong and they just chose not to act on it. So certainly that can happen. The safety guidelines are in place. It's just a function of if they're followed. And that's always an issue. I mean, you could say the same thing for bottled water as well, though. The FDA is going to regulate it, but if a company decides just to take a chance and dodge the regulations and hope they don't get caught, that can happen as well. All right, anyway, I believe this is the last slide. You can ask yourself, what do you drink? Me personally, I don't drink tap water because I don't like the taste. I think it tastes salty to me, but I do drink it occasionally. I drink Sparklets, and I chose Sparklets because they were giving away free baseball tickets if I signed up that day. So I don't really have any misconceptions. So don't think that there's any magic in any particular type of water you're buying. You should buy a bottle of water because you like the flavor, or you think the bottle's pretty. Don't really be misled into this bottled water is this magic potion that's going to make me stronger, faster, and whatever. It's pretty much all of it's water. So you have a reading assignment on this as well as homework. The next exam is going to go up through this material and include the reading assignment on water. Right? I hope that helps and clears things up. You should be able to do the last homework and the reading assignment. Have a good one.